Okay, this week we are going to look at some of the North American qualification contest problems, and I picked some of the perhaps more approachable ones. And so let's start with the easier ones, and I won't spend too much time on it, and then we'll get to some of the harder ones. So the first one is Simon Says. It's actually not that difficult. All you have to do is decide what the number of sentences or commands, and then each sentence either starts with Simon Says or doesn't start with Simon Says. And then if it says Simon Says, then you strip off the Simon Says part and then print the rest. If it doesn't say Simon Says, then don't do it. Okay, so basically, I don't really want to spend too much time on this one. The main thing I would say is to make sure that you use getLine to read this, right? So you would do something like this. You figure out the number of cases, and then you would loop that many cases. And then you probably have a string for S, and then you would, for each one, get line C and S. And this is where the first problem comes, and if you're not familiar with how C++ input works, is that you would have a number, let's say 3, and then you would have a line. And when you read the number 3 here, the cursor, if you just imagine cursor of where to read next, there's a new line here, will be, after you read this 3, will be hanging right here. And then if you were to do a get line, what's going to happen is it will read a blank line here, because that's the first place that stops you from the next line. So the first case, if you do it like this, will just be a blank line, and then you will eventually, the third line, you will not read because you have read 1, 1, 2, and the 3 line. And then this one will not read. So there are a number of ways you can do this. To handle this, one way is to do C and dot ignore. That will get rid of the next one and move you to the next line. Or you can just, another way is just call getLine to basically eat that new line. Okay, so anyway, that's the only real trick. And then you basically says if, right, S dot find, I don't remember if that's the correct case, but let's say it is. Simon Says, like this. It's equal to 0, so that means it starts right at the beginning. Then you do something. And what is it that you do? You want to print the rest of the line. So you have to do cout s dot substring, and then you have to basically figure out how many letters to strip up. It says 1, 2, 3, 4, 5, space 7, 8, 9, 10, 11, because it's a space too. So they stripped up 11 characters, and then if you just do this, that will basically start a substring from the 11th position 11 all the way to the end. Remember that we start at 0 counting, so if you want to skip 11 characters, you start at 11. And that's pretty much it. There's not too much more to say. All right, the next problem that I want to talk about, again, there's not a lot to say. It's called mixed fractions. If you read the problem, basically they tell you that there's a numerator and denominator. They are all positive integers from 1 to 2 to the 31 minus 1, so they're just normal integers, 32-bit int. And then you're supposed to print, you know, the integer part, the numerator of the fractional part, and then the denominator. And it also say, so that makes it even easier, you should not reduce the fraction. So you don't have to divide by the common, greatest common divisor of the numerator and denominator. So what do you have to do? All you have to do really is to realize that once you have n and d, then the 3 numbers that you want, right? You want the integer part, that's called I, and then the new numerator and the new denominator, Well, this is exactly the same as D. N is exactly N mod D, the remainder, and I is exactly um, N divided by D, the integer quotient. And because all of the numbers are positive, there's not even any trickiness going on. You just figure out these three numbers, print them in the right order, and that's really it. Okay, so again, there's a couple of problems that are not too difficult. All right, so now let's maybe look at something that's a little bit more interesting. Okay, so we'll step up a little bit harder now. So there's a problem. This is called quick brown fox. A pangram is a phrase that includes at least one occurrence of each of the 26 letters A to Z. You're probably familiar with this one. The quick brown fox jumped over the lazy dog. Your job is to recognize pangrams. For phrases that don't contain every letter, we put what letters are missing. We'll say that a particular letter occurs in the phrase if it occurs as either uppercase or lowercase. So that's important. Uppercase or lowercase are the same. The input starts with a line containing integer n, which is up to 50. Then those are basically the n cases. Each phrase contains upper and lowercase letters, spaces, decimal digits, punctuations, and so on. Each phrase contains at least one and no more than 100 characters. Then for each input phrase, I'll put the word pangram if it qualifies as a pangram. Otherwise, I'll put the word missing followed by a space, then the list of characters that didn't occur. I'll put them alphabetically. Okay, so basically what you have to do is you have to read those strings, and then again, because there's spaces, you need to use getLine. Convert all, basically record which letter occurs while at the same time treating upper and lower cases the same. And then at the end, just say which ones didn't occur, right? So there are many ways you can do it, but most likely you're going to have a Boolean array that checks which letter has occurred. And that's basically one of the approaches that you can do. And here's my solution. So I'm using an array to see which one has been seen. And I intentionally don't use 26. I mean, you can say, well, if it's just A to Z, why do I have 256 instead of 26? Because I'm basically just going to not bother converting A to Z into 0 to 25 and just use the ASCII value of A to Z. Either way, it's fine. So that's the way I do it. And this function stop basically stops each particular case. So I read the line. Then for each character in the line, I would basically I convert the character and then set the corresponding value to be true in the array. And then basically I'm just looking for anything that is bad, anything that is not seen. So I loop through the whole array from A to Z. If I find something that's not seen, then I print out that character. Now I do need a little bit of trickiness here because I'm using a loop that loops with the characters, but then I convert it to a character before I print it, otherwise I'll print the ASCII value. And then I only print the word missing if I have not found out that it was bad. So I will only print the word missing at the very beginning. And then if at the end I haven't found anything bad, then I print pangram. I would say that this was done when I did this. This is North American Qualified 2015. I think I don't remember if C++ at the time, the ones that we have access to, has the C++ 11 very much yet, or maybe I didn't use it. But there are better ways I can write this now. For example, instead of using a for loop like this, I can say for C. Let me just write it on the side here. You can write for auto C : line seen to lower C equals to true, and you can use SPL stuff and range-based for loop a little bit better. But in any case, what else do I want to say about this? The only other thing here is I reach the number of cases and I do this thing that I mentioned, that you have to eat up that hanging line just so that you won't end up processing the spelling line and missing the very last case. Anyway, so that's this. All right, let me clear. There are many other ways you can do this, but this is the way that I choose to do it. Often with easier problems like this, there are many ways you can do it, but the question is, how do you get it done quickly and correctly, right? And if you're familiar with the C++ kind of all the libraries, and using that to advantage can make your coding part faster. All right, so let's see the next one that's maybe slightly harder. I don't know if it's actually hard. Okay, anyway, Jack and Jill develop special encryption methods so they can enjoy conversation, blah, blah, blah. Let L be the length of the original message, and M be the smallest square greater than or equal to L. Okay, so you have to find the smallest square, perfect square that is greater than or equal to the length of the message. Then you add M minus L to the asterisk to the message, giving a padded message with length M. Then you're going to fill out a square in row major order. That means you basically fill it one row at a time, and then at the end you pad it with stars. Then you want to rotate the table 90 degrees clockwise, and then you read off the message. Okay, so they show you this. And so basically you just have to do this. Okay, and then when you rotate this, you would ignore all the stars. So JEI, AYL, and so on. So basically there's two parts to this. First, you want to find out what is the smallest M that works. Then fill that all in. Then the second part is you have to figure out how to rotate this thing 90 degrees. Okay, so filling it, I guess they tell you, so first of all, the number of, the length of the message is at most 10,000. So you know that the size of this square is at most 100. So really, if you want, you can just do a linear search. There's no need to do anything fancy. There are only 100 numbers to try. You try 1 square, 2 square, 3 square, and look for the first one that it's at least as big as L. If you really want to, I suppose you could take the square root of L and then maybe round it up. But you know, the thing is, when you take square root of integers, you could be stepping into floating point numbers. And if you are able to avoid floating point numbers, it's actually better, even though you might say, taking square root and rounding up is like one line, whereas I do a linear search, maybe it's less efficient. It's actually better not to do square root if you can avoid it. Anyhow, because it's so small, we really don't care how we do this, how we find the square that works. Then you fill it in, and then the question is, how do you rotate this thing? And I mean, you can physically rotate it, or you can just decide to read things off in a different way. So here's what I would say, right? So if you are thinking about, you know, rows 0, 1, 2, 3, and then columns 0, 1, 2, 3, and then you think about rotating this, and this now what used to be rows. So here, the rows in the new one, it's now what columns, but columns, if you think about the columns, it's going to be 0, 1, 2, 3. The rows in the new one used to be the column. I guess that's what I'm trying to say. And then the columns of the new one, it used to be the rows, but in backwards order. So how do you actually do this? How do you produce the output without actually rotating? Well, all you have to do is do something like this for in column from 0, column less than m, column plus plus. Then for in row r equals to what? M minus 1, because now we're moving backwards. R greater than equals 0, R minus minus. And then you do something with, if this is your array A in your original way, then you do something with A bracket C R. Now, what do you need to do? You need to check if it's star. If it's not a star, then you print it. And that's essentially all you have to do. Okay. So of course you can rotate the thing, but rotating things is a little bit tricky because now you have to worry about you probably should get a new array to rotate into, so you don't do things in place. You can do things in place, but it's much harder. And you can figure out how to rotate it with the indexing. Basically, you end up figuring out the same kind of thing that I did, but it's much easier just to print the thing without rotating it. So, show you my submission. This is submission many years ago when I did this contest. And that's pretty much all I told you. The first thing, I figure out the length of the string, and then I just do a linear search. As long as the square of the side is too small, I keep increasing it. Then I fill it in. Okay, so I just loop through the whole array and basically keep updating and get the next character. And if I manage to go out of bounds, then I put stars. And then I just print it the way that I told you. And that's it. And of course, because in multiple cases, I always like to write in the main program, read in the number of cases, and then I just loop through and call a function for each case. And then that makes my function to solve basically just one case at a time. Okay, so that's the what is called secret message. Okay, let's see what's next. Which one is next? Okay, let's look at all about that base. Okay, so to tell you that the base, blah blah blah, so you know what the base 10 system is. The example is base 10 and so on. And in base B, we can use B symbols to represent 0 up to B minus 1, and so on. So you know what this is about. Other bases commonly used is in computation include base 2, base 8, base 16. And in base 16, you use A to F to represent the digits 10 to 15. And in bases bigger than 36, the letter Z represent the value 35. So your job is to determine the bases in which given arithmetic expressions are valid. We define an expression as valid in base B if two conditions are true. First, all operands used in the interpretable in base B as having values in the decimal range 1 to the 32 minus 1. Okay, so now when you see 2 to the 32 minus 1, you have to be a bit careful because this is bigger than a normal in. It's a 32-bit unsigned in. Okay, so you have to be a bit careful here. Second, if the expression is true, any arbitrary expression might be valid in 0, 1, or more bases. In this example, we will only consider bases 1 to 36, where base 1 is unary. Okay, so everything you probably know except for this base 1, which is a little bit strange. And it says, note that following the convention listed above, unary would consist of a single symbol 0. In this problem, unary numbers use the symbol 1 rather than 0. Think of it as tally marks. So 111 in unary is the same as decimal 3, and then 7 ones together in unary is equivalent to decimal 7. So in unary, it's just a bunch of 1s, And then the count of how many ones you have is the actual number. So the input for this problem starts with a line containing integers n up to 20, and then n lines of the form some number followed by some operation plus minus star time, the star divide, y equal to z. And you know also that for each statement there's at least one base that makes it work if you interpret that base. So for each expression, list the bases. Wait. For each statement, there's at least, for each statement, there's at least one base between 1 and 36 such that x, y, and z can all be interpreted in base p as having a value in this range. But you don't know that the operation is correct. For each expression, list the bases in which the expression is valid, sorted in ascending base order, or the word invalid if it's not valid in any of the bases. Use the symbols 1 through 9, then A to Z to represent, and then 0 to represent the bases 1 to 36. Okay, so there are only 36 things to try. So basically the idea is try each of the 36 bases. And for each base, you have to check a few things. First, are the numbers a valid number in that representation? And then if it is, then does the arithmetic operation make any sense? All right. Conceptually, it's not hard, but there's a lot of mess. So let's look at the mess. Okay, so let's look at the code. Again, the first thing I do in my main, I just read a number of cases and then I loop through for each case, so nothing exciting here. Now, what I'm going to do, the first thing is I'm going to have to read everything in strings because I don't know what's going on, what bases I have to try. And then I'm going to have this flag that says whether I found any valid cases. Okay, because if it's not, then I have to, if this remains false at the end, then I know that I have to print invalid. Then I'm going to try all of these 36 times, all of the bases from 1 to 36. And if at the end I haven't found anything, I print invalid. Okay. So now what I'm going to do, I'm going to have a function that will return to me the value of that string in base p. Whatever that base p is, whatever string is, it will return something. And it's going to return a negative number if it's invalid. So this is how I'm going to check that it's invalid. So I'm going to call this function to convert x, y, and z into an integer value. And I'm going to return negative. If any one of them is negative, I know that I haven't found it. Now that if I pass this line, that means that all the numbers are valid in that base. Then what I'm going to do is I'm just going to actually do the operation, whatever it is, whether it's a plus, I compute the results and so on. The only thing that when you have to worry about with divide, it's always divide, right? Divide, you have to make sure that you're not dividing by negative, by 0. And then in this particular case, because the right-hand side has to be, z has to be integer, I also make sure that it's evenly divisible. And if any of those things are not true, I just set the result to be -1 to make sure that there's no way it can match that. And then otherwise the result is the integer division, which is guaranteed to be with no remainders. And then finally I ask if the result that I compute matches the one on the z value, then I know I found it, so I can print out the base value. Okay, but there are a few things that I'm hiding with functions. First of all, this value function, I am actually returning a 64-bit integer. Because I want to use negative numbers to indicate that there's a problem, and I know that the errors, the values can go up to all the way up to 2 to the 32 minus 1. So a normal int would not be good enough, and an unsigned int would not be good enough because I want to use negative numbers to indicate that there is an error. Okay, so let's look at my value. Now, one of the problems I have to worry about is how do I convert digits into values, right? So, F is 15 and so on. And there are a number of ways you can do this. And the way that I choose to do it is just write it all out. It's a string so that the position of the character in this string is automatically the value. And that's my trick, is that the value of a number, of a digit, so I have this special one, the value of a digit, I always have to worry a little bit about this base one, is the X, so basically the value of this is either 1 or nothing, and this is an error. So I also have to indicate that if let's say you're base 5 and you give me a digit 7, then that's not a valid digit, so I return -1. So -1 is sort of my universal error code here. And basically what I do is I look up the digits in here and compare with the base. If it is the right number, I just return the position, otherwise I return -1. And then to figure out the value of the entire number, I use the standard left to right conversion. I start with a value, and then at every step, I figure out the value of the character. If the value of the character is less than 0, then there's an error. Otherwise, I just incorporate by multiplying by the base plus the value of the new digit. And then the next thing I have to also worry about is, have I overflown, right? I was told that a number must sit between 1 and 2 to the 32 minus 1. So this is 2 to the 32 minus 1. I need to make sure that I haven't gone over. Okay. So that's this problem. And then the output, again, there's the trickiness that I have to print out a certain kind of character to indicate what base it is. And so, again, I use the same trick. If it's base 1, I print 1, 2, 3. I just basically print out, have a string like this that indicates whatever, if basically the base, it's going to be used to index this string to figure out what character to output. You can, of course, write it in some kind of if statement, switch statement, whatever it is, but or maybe arithmetic calculation. But for me, this was a bit easier to figure out, and I don't have to think about this too much. All right. Now, I want to talk, before Bobby's got, I want to talk about quantum pieces. Okay, so I'm not going to read the whole problem, but basically, you have a bunch of paper fragments. Each fragment happens to perfectly contain a single subway station and identifying all the other stations they connect to. Each connection between stations is bidirectional, so you can go either way. So in other words, each of these fragments gives you a node in the graph and all its neighbors. Using all the available fragments, your task is to determine the sequence of stations you must pass through in order to reach your final destination, or state that there's no route if you don't have enough information to complete your journey. So there are 32 pieces, which is not that much. The only tricky thing is that the stations are given by name. So you need to have a way to convert names into a number between 0 and 32, basically, or 0 31. And that's it, you build a graph. You're supposed to go from they will also give you a starting destination station. And then all you have to do is basically find, how do I call it? Find a path. And also they tell you that it's guaranteed that there's at most one simple route from the starting to the destination station. So you don't have to worry about having a cycle and having multiple ways of going. So once you build this graph, it's just a matter of doing a relatively simple graph first. And you can use any method, DFS, DFS, or anything else. Really doesn't matter. So I just want to maybe quickly show you my solution. This is pretty much, you might see that this looks like a lot of code, but it is really just a, how do I call it, the routine, because you just bring it from the code library. I think this is called BFS path in the code library, and I just paste it in. Right, so this is really just the whole thing. And then, so up to this point, the first 62 lines or so is just library code. I didn't really write anything. And then I write a single piece of code that basically takes the name of a station and map it into an integer. Basically, what I have is a map that maps strings to ID integers. And if you want me to give you an ID of a station, the first thing I'm going to do is ask, have I seen this before? If I've seen this before, I just return the ID. Otherwise, I give you a new number, basically. What else do I want to say? Okay, so anyway, I create a graph. I don't know why I did times 10, but I did put a comment just in case I allocated way more than I need. Then I have a map like here. I have a vector of names. Why did I care about the names? Oh, because I have to print out, at the end, I have to print out the names of the station. So I need to remember how I go from numbers back to names. And then, yeah, I just basically read the n chunks. For each chunk, you read in the name of the station, and then you read in all the names of the things that it attaches to, and then you add an s. There's a slight trickiness, I guess, to parse this input because you don't know how many names there are on a line, but you basically just use a string stream as one way to deal with it. Then you read in the source and destination, figure out the index, and then you run the BFS code. There is the P that remembers path information, and then basically you say, have I seen, if the destination have not been visited, then you say no row found. Otherwise, there's this function called getPath that will give you the list of IDs that are needed to go from one place to another in the path, and then just print it out. So if you know if you've seen this code, if you know how to use it, then really it's very easy. But this problem itself, if you're familiar with graph traversal, it is not that bad. You can use recursive search with DFS2, and then when you find a destination, then basically when you back up your recursion, you can print things out. But you have to remember that when you print things out, you're printing things out backwards. So you probably store things, either you store things in somewhere and then print it in reverse, or another way to do it is to actually do a DFS search from the destination to find the source, find the start, and then when you back out, you're printing in reverse, but since you're searching in reverse, then you're basically printing forward. Okay, the last problem, it's Bobby's batch, and this one, it's a little bit more mathematical, but if you have taken some, I guess stat 70/70 or maybe higher stats, you probably have seen this before or something similar. Okay, so basically you have S-sided, you have a bunch of, you have one S-sided die, each side is equally likely. You want to obtain a value of at least R on at least X out of Y rows. So what is the probability? And then, okay, if you can figure out what the probability of you achieving this is, then the rest of the question is relatively easy. Basically, what you do is you say, well, if the probability is a half or whatever it is, then they tell you W is the multiplier that you win if you succeed. Then you want the probability times this, which you expect the value to be bigger than or equal to 1. No, sorry, if it's bigger than 1. So anyway, the main crux of the problem is to figure out the probability of how likely this is going to happen. There are at most 20 dice in this dice. You at most roll it 10 times. So let's think about this. Okay, so S-sided die row at least an R, and S is at most 10, no, at most 20, right? And then out of Y rows, at least X successes, and Y is at most 10. All right. The word at least makes it a little bit trickier. It's a little bit easier to talk about exactly a certain number of success, so we'll change the problem slightly. And we'll see how we can do this. Make use of this slightly different problem. So we'll say exactly X out of Y rows, we row R at least R. Okay, so what's the probability? And if you have seen probability distributions, and this is exactly what we call a binomial distribution. If you've never seen that, that's fine. We'll talk about that a little bit. So basically what you do is you say, for one single row, what is the probability of success? Success means that you row at least R. Well, it's going to be over S, because you have S sides. How many rows, if you think about it, it's that this many S plus 1 minus R sides that are at least R. Okay, so if you have to just do a simple example, let's say S is 10 and R 7. So 7, 8, 9, 10, there's 4 of them that are at least 7. And if you plug this in, 10 plus 1 is 11, minus R is 7, which is then give you 4 out of 10. Okay? So something like this. And then fail would be exactly, we call it Q, 1 minus P. Okay? If you want to simplify, is S R minus 1. Now the problem, of course, is you need to row a Y times. So let's say let's just make things concrete. Y is 7, and I want to know exactly how many ways can I row exactly 3 successes. Well, so what you have to think about is which one of these 3 are successes and which one of the other 4 are fails. Well, if there's 7 of them, then there's 7 to 3 ways of arranging which row is successful and which row is failing. And for each of these ways, you're going to have to make sure that 3 of them are successful and 4 of them are unsuccessful. So altogether, this is the probability that exactly 3 rows are successful. And if I generalize, then it'll be P and Q will be here, and then it'll be Y choose little x, P raised to the power x, Q raised to the power Y minus x. And that's the probability of being successful exactly x times, exactly. But we don't want exactly, we want at least. So how do we deal with this? Well, if you know, because Y is fairly small, so if they tell you, let's say Y is 10, and they want at least 7 successes, well, then you just ask the same question, exactly 7 of them, exactly 8 of them, exactly 9, exactly 10, and then you add them all up, because the 7 is the same as exactly 7 or exactly 8 or exactly 9 or exactly 10. So all you have to do is basically break that into the different cases and then add up the probability. And this is a pretty standard trick. that if you can make things a little bit easier this way, right? By making exactly, you can solve the problem easier. And then if you loop it by picking up in all the different cases and adding it, that makes the problem easier. Okay, so what else do I need to say? Now, the only other thing that I need to say, I suppose, is at some point we're going to say the probability times W has to be greater than 1. Everything is integers. So the question is, is it possible that we avoid using any floating point arithmetic? And we have to think about what's going on here. So this y over x is an integer. It's a binomial coefficient, it's an integer, no problem. P over q, it's going to have a denominator of s. And the s, the amount of s in p and q in the denominator, it's s, x, and y minus x. So in any case, the denominator here is always s raised to the power of y, which is at most 20 to the 10. Now, 20 to the 10 is pretty big. And it's going to be bigger than, let's see here. So 20 to the 10, it's going to be bigger than even 64-bit integer, I think, because well, we can quickly look into this. Is that right? Maybe I'm wrong. Yeah, this is 20 to the 10, 2 to the 64 minus 1. Oh, okay, I was wrong. So what you could do is to basically just compute all of these things, P and Q and X, Y and X, without the denominator. Okay, you can forget about dividing by the S, because you know that every single term, every single thing that you compute will always have S to the Y on the bottom. So at the end of the day, when you do this computation, right, it's the probability times W bigger than this, bigger than 1, you are going to move, you're going to basically take this S to the Y and move it over to here. And if you do it carefully, you should be able to handle everything as an integer. And then you don't have to worry about any kind of floating point error. Now, I did do it with floating point numbers, and it turned out to work, but I don't know if that's because I was lucky or because it turns out the way whether there's any guarantee that it works, but here it is. And the only other trick is, if you haven't seen this before, binomial coefficient is probably best to pre-compute them all with a Pascal triangle. I'm not quite sure why I went up to 20 when I did this, but anyway, you only have to go up to 10. So anyhow, so this is the this set for this week, and next week we'll have another set based on North American qualification. All right. Stop the share, stop the recording.